Here's a visual summary of your deep learning model. Input layer, convolutional layer, max pooling layer, convolutional layer, max pooling layer, flatten layer, dense layer, output layer, training process, forward propagation. Data flows from the input to output layer, applying weights and activation functions. Loss calculation, compares predicted output with actual labels. Backpropagation, adjusts weights to minimize loss. Optimization, uses Atom Optimizer to update weights and biases. This structure allows the model to effectively learn and classify the handwritten digits from the MNIST dataset. Lines 1 through 6, importing libraries. TensorFlow STF, imports the TensorFlow library for building and training neural networks. From TensorFlow, Keras, datasets import MNIST, imports the MNIST dataset for handwritten digits. From TensorFlow, Keras, models import sequential, imports the sequential class for creating a linear stack of neural network layers. From TensorFlow, Keras, layers import Conva 2D, max pooling 2D, dense, flatten, imports specific layers used in building the convolutional neural network, CNN, model. Conva 2D, performs 2D convolution operations on the input image. Max pooling 2D, reduces the size of the feature maps by taking the maximum value in a specified window. Dense, fully connected layer where each neuron receives input from all neurons in the previous layer. Flatten, converts multidimensional data into a 1D vector. Lines 8 through 12, loading and preprocessing MNIST dataset. X_train, Y_train, X_test, Y_test, equals MNIST. Load_data, loads the MNIST dataset into training and testing sets. X_train and X_test contain the image data, while Y_train and Y_test contain the corresponding labels, digit values. X_train equals X_train, reshape, 60,000, 28, 28, 1, astype, float 32 feet, 255, reshapes the training images to have a single channel, grayscale, and normalizes the pixel values between 0 and 1, originally 0 to 255. X_test equals X_test, reshape, 10,000, 28, 28, 1, astype, float 32 feet, 255, reshapes and normalizes the test images in the same way. Y_train equals link to tf.keras.utils.to_categorical, Y_train, 10, converts training labels to one-hot encoded vectors. One-hot encoding represents each digit class, 0 to 9, with a vector of 10 elements, where only the element corresponding to the digit is 1 and all others are 0. Y_test equals link to tf.keras.utils.to_categorical, Y_test, 10, converts test labels to one-hot encoded vectors in the same way. 14 through 25, defining the CNN model. Def create_model, defines a function to create the CNN model. Model equals sequential, creates a sequential model where layers are added one after another. Conva 2D, 32, 3, 3, activation equals ReLU, input_shape equals 28, 28, 1, first convolutional layer with 32 filters. These are learnable kernels that extract features from the image. Kernel size, 3, 3. The size of the filter window that slides across the image. Activation function, ReLU, rectified linear unit, introduces non-linearity. Input shape, 28, 28, 1, specifies the input image dimensions, height, width, channels. Max pooling 2D, 2, 2, performs max pooling with a pool size of 2, 2, reducing the image size by half while retaining the most important features. Similar layers follow. Another convolutional layer with 64 filters, followed by another max pooling layer. Flatten, flattens the output from the previous layer, usually a multi-dimensional feature map, into a 1D vector suitable for fully connected layers. Dense, 64, activation equals ReLU, first dense layer with 64 neurons and a ReLU activation function. Dense, 10, activation equals softmax, second dense layer with 10 neurons, one for each digit class, and a softmax activation function. Softmax outputs probabilities for each class, ensuring they sum to 1. Model, compile, optimizer equals, atom, loss equals, categorical underscore cross entropy, metrics equals, accuracy, compiles the model by specifying. Optimizer, atom, is a popular optimization algorithm for adjusting the model's weights during training. Loss function, categorical underscore cross entropy, measures the difference between predicted and true classes. Function, train underscore model underscore on underscore device, device underscore name. This function trains the CNN model on a specified device, CPU or GPU, and measures the training time. Device context, the with TF, device underscore name, line sets the context for training the model on the chosen device. This ensures all operations within the indented block utilize the specified device. Create model. Inside the device context, the function calls model equals create underscore model to create a fresh instance of the CNN model we defined earlier. This ensures each training run uses a new model instance. Training. The function then measures the training time. Start underscore time equals time. Time captures the starting time before training. Model link to .fit, x underscore train, y underscore train, epochs equals 5, batch underscore size equals 64, verbose equals 0, trains the model. Here's what this line does. X underscore train and y underscore train are the training data, images and labels. Epochs equals 5 specifies the number of training iterations, 5 in this case. Batch underscore size equals 64 trains the model on batches of 64 images at a time. Verbose equals 0 suppresses the training output for cleaner execution. End underscore time equals time. Time captures the ending time after training. Finally, the function calculates the training time by subtracting the start time from the end time. Return end underscore time, start underscore time. This value represents the time it took to train the model on the specified device. Comparison on CPU and GPU. Training on CPU. CPU underscore time equals train underscore model underscore on underscore device, CPU, 0 feet. This line calls the train underscore model underscore on underscore device function with the device name, CPU, 0, which specifies the CPU. The function returns the training time, which is stored in the CPU underscore time variable. Print, f, time taken on CPU, CPU underscore time, 0.2 f, seconds. This line prints the training time on the CPU, formatted to 2 decimal places. Training on GPU. If TF, config, list underscore physical underscore devices, GPU, this line checks if any GPUs are available on the system using TF, config, list underscore physical underscore devices, GPU. This function returns a list of physical GPU devices. If the list is not empty, meaning a GPU is present, the code inside the if block is executed. GPU underscore time equals train underscore model underscore on underscore device, GPU, 0 feet. If a GPU is available, this line calls the train underscore model underscore on underscore device function with the device name, GPU, 0, specifying the first GPU. The return training time is stored in GPU underscore time. Print, f, time taken on GPU, GPU underscore time, 0.2 f, seconds. This line prints the training time on the GPU, formatted to 2 decimal places. Else, if TF, config, list underscore physical underscore devices, GPU, returns an empty list, no GPUs are found, the code within the else block is executed. Print, GPU is not available on this system. This line prints a message indicating that no GPU was found on the system.